Okay, welcome back. I think last time we were taking a look at homework 3, module 3. But I think now we're starting project 3, at least timeline-wise. Were there any questions left from like homework 3 or concepts like module 3 kind of work? We're jumping into project. All right, I can check in and see what people are working on and then come back up. You said something didn't open, but that's not a chance to review.
This is what I get. Okay. And I close it, and now I'm doing it.
Trying to click file. I don't think that one, sometimes that'll happen because there's a note, like a PYNB and a markdown file. So it tries to keep them in sync, but sometimes it'll say
In
like,
terms of like, the reason it happens is I try to go over to last point.
okay.
Because I somehow deleted one of the key cells right here, like one of the break cells.
Oh, okay.
And then I can kind of go back, and there's no one there.
C, so if you just hit the C button, no, just the C. Yeah.
Oh, okay.
Yeah. So if you click like help, it's not C. It's just missing. All the different things that you can do while you're in here. Yeah.
I really wonder what would happen
Yeah. So if you're actually like if you're typing it, that's edit. And then it's just a blue thing where it's selecting a cell. Yeah.
So, I think there's those bills.
Other than access, have you had trouble with like concepts?
No, I was like kind of looking through it, like, I was just.
Okay. Yeah. Be working through.
I'll be honest, I haven't even done one in like 1.2 of the whole thing, so
Of your homework. Okay. Okay. So, is everything okay?
Yeah. Just busy.
Looking at convergence rate. Oh, looking at the project.
Yeah, yeah, yeah. Get that to work.
We actually don't have like a derivative function.
Okay.
So we use like modified CP, which got approximate.
There's a question asks you, and that's what is it that helps conversion?
Oh, alright, hang on.
Yeah, yeah. Oh, yeah.
For the challenger on
Okay,
not the right. That one,
I was trying to
or that one's feeling, if you look at the curve here.
Yeah.
So you take that point on the curve, you draw a slope like a point.
Yeah.
It would end up there.
Okay.
And then from 0 would go to like infinity. So it's a divergent. So that's supposed to happen.
Will work.
It will work in some places. Like if you get 60 degrees,
I did.
then that should converge. If your derivative is correct.
Okay. Yeah, no, but it's,
I don't know. Okay.
I'll do that.
Okay, so got it. But homework was done. No questions. Okay. Yeah. Okay. Yeah. Yeah. Right there. Okay. Yeah, what did we change? Did it look like the same code? Had you copied this? Maybe, yeah.
They don't have nothing to do with it.
A lot of times I'll forget.
No. I think that was my plan. I mean, always good to do it. It's really like this. They're all.
You want to take photos of them? You think they would just be?
Use an error, if it's an error, I can show you the next line has an error.
Yeah, that's showing us
Oh my
It
god.
could be network, could be missing. It still ends the next line.
Did I?
Okay.
Thanks, you.
Okay.
Mostly not that. Was it online administrative?
Yeah.
Yeah, I can see that.
The same exams. And I just have them.
Genuinely?
But my folder is just a huge mess. It's like this thick numbers. And I have to somehow remember what to tell her to take pictures of.
You're not labeled. You don't label it. Great with ACT graduation.
Let's see what it is. It's complicated. So I do have pictures of my they're going to submit them.
Yeah.
That's a shame. Hold on. Take a look. See if I just do it. Yeah.
All right, so there were questions on homework 3, at least going around, checking in with people. Let's go down to skipping over some of this. Part 3. Is this? So in this last section, we're looking at like root finding methods. So we can do integration methods, and this was the same kind of problem that came up on project 1, where we could do an integration, we could find that temperature at any point in time, but then the question was like, how do we find a temperature, the time for a given temperature? And that's where root finding methods kind of come in. So first thing that came up was like Newton-Raphson just wasn't working, and here we'll do a def and what's our function? Oh, did something wrong, huh? Oh, it should be a 1 plus. There we go. All right. So there's our like sigmoid curve, just taking the function. So if I'm trying to find like what is the temperature for 50% failure, like what's our cutoff here? One way to do this is like we have a function we could just do a bunch of math, like invert this function. It wouldn't be, it's not easy, but it's not the end of the world. Like we can do that. Or we can use ink search and Newton-Raphson, these different methods. It seemed like ink search, people were able to kind of get this to work, but Newt-Raph was having trouble. Main thing there is this Newton-Raphson. Let's go down. Newt. I'm going to copy it right into the homework. We need a function and we need its derivative. So the derivative of that function. And again, you can do it by hand, or like we're using Python. We could do symbolics. Has anyone tried SymPy before, like symbolic Python? Do you want to see it, like how to do math? I forget. SP? All right, we'll try that. Oh yeah, I need SP. All right, so at least if I want to do like symbolic kind of math in Python, I can call up SymPy, like symbolic Python library, and at first there's not much of a difference. The only thing is like it takes a function, like an actual math function, it can pretty print it, like make it look like an actual function. There's some fractions. It kind of looks the same as this thing up here. But now the magic is we can say sp dot, is it derivative or differentiate? Let's double check. Diff. So now it'll give me like the derivative of a function that I just typed in. And it's still like symbols. It's not taking a finite difference. Like it's an actual function that I can evaluate. And let's do this. I'm just grabbing. Oh, that doesn't look right, right? I didn't type it in right. Squared. That's an F1 plus 1. F plus 1. E to the negative 2A0. Oh, positive 2. A0 minus 2T A1. There we go. That looks a little better. Of like, we have our function, which starts at 0 slope, goes down, and then 0 slope again, which is what we have down here. Like 0, change in slope, back to 0, and then so newt graph of our sigma and d sigma, and then we just need some initial guess. So let's call our initial guess 0. And did you get an error if you got to this point? Like, did you get any kind of, technically it's not an error, it's just a warning telling you like it's not, things are not as you expected. Anything like this? What is this output? Like, why is it a whole bunch of not a numbers and then a 49? What is that telling us? Oh, you know what I should have done? Like right now I have sigma defined, but really I'm trying to find where sigma is 50%. So I should have a lambda of t sigma t minus 0.5. It's not going to change the answer. It's still going to have, here we have something a little different, like infinity, negative 0.5, not a number. And coming back up here. That last, so that 49 is telling us like it went through all 50 iterations and that's the best it could come up with. The EA is telling us what that current error is, like what's our change in error, and for the most part we've just been hitting 1/2 over and over and over, so there's no change. And then the actual like function of XR is in here, or I guess that one's negative 0.5, and our error is just not a number. This infinity is the best guess that Newton-Raphson has right now. And if I look at this plot and think about like, if I'm right here and I want to draw, based on the slope and where I'm at, I want to draw a line to that 50% mark. So right in here. The slope is 0 or pretty close to it. So it's going to go way off into infinity. And then that slope is going to be 0, so it's going to come back way out here. So it's going to keep diverging. Meanwhile, if I chose something like even here, that should get me a lot closer to my answer, the answer that I'm looking for. So instead of 0, let's try initial guess of like 50. I still get like not a number. 55. All right, we'll go 60. And as long as I'm anywhere within within like somewhere that it looks like it's going to converge, then it will. And this is the benefit of these open methods, is that they converge really fast. Like you only have to evaluate this thing 4 times to get a really small error, but you do need to be somewhere close to, and it's the same for Newton-Raphson and the modified secant. Like if your initial guess is way off, or the function does anything kind of weird, it's hard to converge to like this like final answer. All right, so continuing on with like, we have functions, how do we evaluate them? Let's see, I have some of this written in already. So I'll leave my fall drag equation. So the shooting method, this is a way of like combining both a root finding and an integration method, because the idea behind it is like, I know what the initial value is and I know what the final value is, but I don't know what that initial slope is. That's the general idea of a shooting method, is like, what was that initial speed that led to that final position. This also comes up for boundary value problems like heat transfer and all of that. One way to solve them is with shooting methods like this, where you guess what the slope is at one boundary, and then try to match the boundary condition on the other side. And Runge-Kutta, we can use Runge-Kutta. So main thing here is we're trying to predict this motion, these red dots. So I know what the initial position is and I know what the final position is. That should be enough information to get the rest of them, as long as I can get that initial speed at 1.48 seconds. And trying to grab this guy. So there's our Runge-Kutta. Okay, what I'm gonna do here is say, remember time can be any time we want. It's an independent parameter. So I'm just going to set it equal to the initial to the final time. So I0 to IE, which is this kind of 1430 to 2051. My initial and my final like bounce position is going to be at time 0 and time -1. So total time span is going from t bounce 0 to t bounce -1. I'll make 50 steps, and each step is going to have same time step size. Now I can start setting up my numerical solution. So I'm going to initialize an array, just fill it full of zeros. I'll make an initial guess. Well, let's call it, let's say our initial guess is 3. 4.1 something is, I don't know where it came from. So my initial guess for velocity, we'll call it 3. My initial position, I know that one. That one's that y bounce of 0, the y0. then I can fill in that numSol drag. I can add based on the initial speed, which is an initial guess, and the initial position, which is real. I can see where I end up at the final time. And with initial guess of 3, I'm pretty darn close, but there's definitely an error. This black line is not ending at the same spot as that blue square. And one way to go about this, at least what we had done in the first module, was just keep guessing. Like 3 is pretty close, but not fast enough, so maybe it's 3.1. 3.1 is too fast, so now it's too high. Like the black line is not matching. But instead of just guessing and checking, I have these root finding methods. So I can define a function like f of v. If I enter a v, it'll give me the difference between my final position calculated and the actual final position. And this one I grabbed from the reading, like this f of v. But for the most part, it's doing exactly what we had done before, where we say we have some time, that's what we define. We're going to create that time step, initialize our conditions. Now this V0 is not some constant. V0 is the input. So we're inputting, so if we give it a 3, it'll tell us how wrong we were. If we give it a 3.5, it'll tell us too fast. And we can try that out. So with a guess of 3, we were too slow by 2.6 centimeters per second. Or 2.6 centimeters. That's how far off we were, sorry, because it's just telling us the final position minus the actual final position. And then when I said 3.1, I was too fast and ended up 3.5 centimeters too tall. So it's probably somewhere in the middle. This mod secant method, grab it here. It uses the same like function and derivative that Newton-Raphson does. So it's still using like slope and intercept to find an answer. The only difference is there's an actual like delta x value in there, like evaluate the function and then find it. The derivative is this the function of x plus dx minus f of x divided by dx. Sure enough, when I run that, it'll give me 3.04, so that's my initial speed, so that the slope is the right slope. And since I have that, I can go back to my initial plot where I said this was 3.1. Let's just plug in the actual 3.04. And now my plot, that black line goes through every one of those blue points in this plot. So it seems like it's the right, and the only thing that we used was initial position and initial slope. And then the rest of this all follows from numerical integration. So it seems like we did something right. Like it looks like the same function now. Cool. Anything else coming up as I was going through some examples? couple minutes left in class, I can give like the overall tour, kind of what we're doing in the project, like why am I asking certain things, like what are these things even asking for. So the general process here is that we want to create a simple model that can be verified. So, and this is probably what you're doing in senior design with your unit problem, at least hopefully. It's like you create a problem, you know that there is a solution for it. And that's what we're doing here. It's like the semi-real problems that we have, mass times we have like acceleration that depends on mass, but mass is changing, and we have gravity and drag, at least the simplest kind of 1 degree of freedom problem. That one, there is no like general handwritten solution for it. So this Russian scientist, rocket scientist, came up with this idea of like, what if gravity and drag, what if we could ignore those? What if those are small enough that it's just a function of mass and speed? So that one does have a solution. So we'll call that our simple rocket. In the simple rocket, we can actually converge to a known solution, and then we're good. So if we can show that our integration methods are the same as like Tsiolkovsky, this like brilliant rocket scientist methods, then at least we know we're doing something right. So that's verification step. Once we have a verified model, in part 2, now we can change our, because for us, changing the differential equation is pretty easy. We can add a drag, we can add gravity, and it doesn't change our process. It's not like we need to go back and rederive all of our equations. We're going to use the same integration method that we just used in the first part. We can even show that 2 different ones produce the same output. So we're kind of, at first we verify with another equation. Now we're verifying 2 different methods, like one implicit, one explicit method. Finally, we can do something like actually interesting and say, I have a function, I know how to integrate it. It is a predictive model. Like I can, if you give me any mass flow rate, I can predict any height, any final height. So now we can reverse engineer and say, all right, we want it to explode at 300 meters. What mass flow do we need? Now we go back to that root finding method that we just looked at for the homework, where we're trying to figure out like what's a good way to get to that final value. So ink search works, and then the other one that we can try is the modified secant. Anyway, that's the real high level tour of what we're doing. Verify, change the function, cross verify the 2 integration methods. It doesn't matter what integration method we use, but at least it'll be the same answer, and then solve a problem. That should be, if you're doing any kind of predictive model, whether it's like ANSYS, CFD, or any of those, that should always be the same process. Here it's kind of a simple, well, it's not simple, it's rocket science, so it's not even simple here. So, but it's at least something. We have a function, right, that we can solve for. But every time you do like a numerical method, there should be some step where you verify, like, all right, it seems like it's working because it's doing what I expect it to. And then as you add little factors to complicate it, you can at least show like they don't change. You can use different methods and get to the same value. And then the last step is actually doing what you wanted to. Do some engineering. Cool. Anything else? I answered all the questions that you didn't have. And we'll be back on Monday. Yeah, Friday we're off, and then Monday we're back. Thanks a lot.